configurations on the market, it's not surprising that manufacturers have various methods to address in-vehicle monitoring and diagnosis of engine management systems. These range from the very early systems with limited diagnostic ability to a modern full house system where OEMs spend vast amounts of time and resources developing diagnostic software to complement their engine management systems. For efficient and accurate diagnosis of these systems, it is vital that any technician working on them have an in-depth understanding of the type of diagnostic approach taken by the vehicle manufacturer. With the introduction of basic engine management systems, we saw the gradual phasing in of vehicle onboard diagnostics, or OBD. But what exactly is OBD? How is it used? And why have vehicle manufacturers adopted various forms of OBD along the way? Initially, manufacturers took many different approaches to vehicle emissions and performance, including the adoption of systems that offered some level of engine management system diagnostics. These had limited capability. These early systems can often be identified by the variety of self-diagnostic approaches used, with the different test equipment and connectors required for each make and model. They were rather primitive in their fault identification and lacked the protection of key emission components like the catalytic converter. From these early vehicle systems, the need was born for a more coordinated and targeted approach to vehicle diagnostics on a global scale. The key players in this process and early adoption of these new technologies emerged out of the United States. In the early 90s, the California Air Resources Board, or CARB, and later the US Environmental Protection Agency, encouraged vehicle manufacturers to comply with specific emission laws, including the adoption of a self-diagnostic program capable of identifying an emission-related fault in the onboard computer systems. This was later referred to as Onboard Diagnostics version 1, or OBD1. Around the same time, the US Society of Automotive Engineers, or SAE, developed what is now known as the standard SAE J1962 16-pin OBD diagnostic connector, which would later become mandatory in OBD2. The early OBD1 type standards were ultimately developed to encourage OEMs in designing reliable emission control systems that maintain effective emission levels. Vehicles that were manufactured to comply with OBD1 type standards were now required to display a failure notification or fault code when an emission-related component failed. So now we would be notified of failures like a defective sensor or actuator on an engine management system, the early stages of onboard diagnostics. Vital emission components like the catalytic converter were not provided with adequate protection under OBD1, and only basic system monitoring took place. Also, vehicles equipped with these early systems typically used OEM-specific communication protocols and error codes. These systems varied considerably from one manufacturer to another. The time frame and likelihood of OBD1 adoption into countries outside the US was a slow and progressive process, with several large countries taking many years to align their local laws and standards to OBD1. Due to the staggered rollout of laws and compliance regulations, this resulted in differing OBD specification levels in markets outside of the US. As an example, you may encounter one vehicle of a particular model year that is fully OBD1 compliant, even though the local laws at the time did not require this. Then you might find another vehicle at the same model year that only has very basic OBD, meeting the minimum specification at the time. So as a technician, you may see some vehicles with only basic flash codes for diagnostics, which may have met the minimum specification, while others of the same model year had full OBD1 systems, including the SAE 16-pin OBD diagnostic connector. Care must be taken when working on early systems, as the OBD diagnostic connector may not be compliant with the later OBD2 requirements. This could result in damage to the vehicle communication network or scan tool if an incorrect connection is made or the vehicle is incorrectly identified during model selection. Be aware of some vehicles with partial implementation of OBD2, being referred to as OBD 1.5. This is an unofficial tag given to some models that were in the transition between OBD1 and OBD2, based on their specification levels. In many cases, this may be country specific due to the time lag in alignment with OBD1 and the timing of new models versus the phase-in of local laws requiring vehicles to comply with OBD2. Due to increasing demands for lower vehicle emissions and the requirements for more standardised information and vehicle access, the US bodies including CARB, EPA and SAE introduced Onboard Diagnostics version 2, or OBD2, in the mid-90s. This was a major step forward from OBD1. This new OBD2 standard was like having an enhanced diagnostic monitor built into the engine management system. OBD2 was a critical step forward in defining the requirements for onboard diagnostics and how OEMs were to meet the emission requirements over the vehicle's service life, as well as providing new standards for onboard diagnostics. OBD2 was designed to closely monitor and detect electrical, chemical and mechanical failures in the various control systems, which may affect vehicle emissions. Like version 1, the rollout to other markets of OBD2 would take some time as governments look to adopt some or all of the OBD2 standards. The technical requirements of OBD2 were established by the SAE in the US and the International Organisation for Standardisation, who were responsible for the adoption of OBD2 into European markets. This occurred around model year 2000 vehicles. The adoption of OBD2 into the European market was not without some changes. However, the key elements and related standards of OBD2 were integral in the European standard, EOBD. In Japan, we saw the introduction of JOBD, or Japanese Onboard Diagnostics, which closely mirrored OBD2 and occurred around the same time. This was then progressively introduced to vehicles destined for export. Other markets outside the US and Europe have typically adopted the European standard EOBD for vehicles in their market or country. OBD2 was in fact reviewed and updated around 2005, which was then rolled out to other world markets. OBD2 and EOBD use a different criteria in determining if the vehicle emissions are outside a limit or threshold, which would indicate a fault. Under OBD2, the criteria for identification is typically 1.5 times the standard which the vehicle was designed to comply with, also referred to as the US Federal Test Procedure. Whereas under EOBD, the trigger activation is based on the vehicle exceeding specific emission limits. With both OBD2 and EOBD, these emission levels are modelled or calculated based on the engine operating conditions and the actual readings from various vehicle sensors, including the oxygen sensor. As a significant step forward in vehicle onboard diagnostics, OBD2 is not just limited to the control of emission levels. OBD also includes a number of the SAE standards, which can be broken down into key elements such as the protection of vital emission components, engine control unit security, fault recording via freeze frame data, driver notification via a malfunction indicator lamp, and many more. Keep watching this series, where we will explore additional features of onboard diagnostics, an integral part in the emissions strategy for any modern vehicle. It's always good to brush up on vehicle diagnostic monitoring and understanding that this technology is critical to the integrity of the engine management system. So get on board with diagnostics and keep learning. Thanks for watching.